Yeah. Thank you for the nice introduction, and thank you for the invitation to this nice workshop in this pleasant place here. And the organizers did a good job in organizing, and especially in the schedule. You see here I will focus on a mathematical view on full waveform inversion. This morning we have seen a computational view on full waveform, and we have seen how which challenge you have to face if you want to really compute things. So here I'm more from the mathematical side, and yeah, this is the thing I can do. Okay, so you all know what's all about. So in seismic imaging, we want to reconstruct the interior of the Earth from the measurement of reflected wave fields. To this end, a wave is initiated at a source here with indicated by this red point. It travels through the ocean, enters the Earth, gets reflected by the interior structure, and the reflected waves are picked up by receivers. So we have reflection data and not transmission data, though this is a difference to ultrasound tomography. And each receiver here measures a time-dependent signal called a seismogram, and from all these seismograms together, you want to conclude what is the interior inside. And the results I will report here have been obtained with my collaborators, which I would shortly like to introduce. Thomas Bohlen is from KIT Geophysics Department. Roland Griesmeier, Andreas Kirsch, and Christian Wieners are from Math Department. Lingli Gao is a former postdoc in geophysics. Lukas Pironek is a current postdoc. Uwe Zeltmann and Christian Reinbay are both PhD students, a former and a current. And we collaborate with Matthias Eller from Georgetown University. Yeah, here's a short outline of my talk. We will start with a little modeling. We will derive the viscoelastic wave equation from first principles. Then I will give a mathematical formulation of full waveform inversion, and I will shortly report some of our results which we found. And then I will dwell a while on the tangential cone condition, and I'm thankful to Barbara that she already introduced the tangential cone condition. So I will motivate why it is important for solving nonlinear inverse problems, and I will show you, that it is satisfied here in the acoustic regime. And then I will end with some concluding remarks. So, wave propagation in viscoelastic media. The wave equation couples the particle velocity here, which is vector valued, together couples with a stress tensor, which is a 3x3 symmetric matrix, over our propagation medium D, which is a bounded Lipschitz domain. And the first equation we have here fits perfectly to the place because it is Newton's second law, balance of momentum. So we have here acceleration times mass, rho is the mass density, is equals to force. We have an external force, and we have internal force. The divergence here is taken rho-wise. And then, of course, we need a second equation for sigma. And here we take into account that waves propagating in the Earth exhibit damping, loss of energy. And this is done by a retarded material law. The state of stress at time t depends on all deformations undergone in previous times. And this is accounted for here by this time convolution integral. And also we have an external source here. So epsilon of v is the linearized straight range, so it accounts for the deformation of the material. Then you apply a time-dependent Hooke tensor to it, and then you get the stress. And yeah, F is the volume force density, G is the so-called external moment density. And then we just take the time derivative, and we end up here with this second equation for the time derivative for sigma. Okay, we are not finished yet, because if you want to do computations, yeah, you have to be more precise on this C here. So you have to model it. This is something which depends on the material, on your medium. And here in geophysics, they use the so-called generalized standard linear solid rheology for isotropic media. However, we can also model anisotropic media. So here our Hooke tensor has two terms, basically, a time-dependent term. Yeah, L sums here. L is a number of damping terms. This is a modeling parameter, and these tau sigma L's are called relaxation times. And you see, if time increases, this vanishes, this part, and so here this describes the material, the relaxed version of the material. So the parameters mu and p, which enter our Hooke element, are therefore called relaxed S and P wave moduli. They are closely related to the pressure wave and shear wave velocity, as we will see in a minute. And further, we have parameters, so functions actually, Ts and Tp, which model the attenuation. Okay, still, if you go back, you see that we have to face here this integral, this convolution integral. We can get rid of this integral by introducing so-called damping tensors. It's just the definition here. It's again a convolution with respect to t. And then we decompose the stress into this into these damping tensors and the remainder term. And simple differentiation shows that we get finally a first-order hyperbolic system for the particle velocity and for these sigma 0, sigma 1 to sigma capital L. I'd like to stress the fact that these sigmas with an index have no physical meaning. They are interior parameters. Only their sum is a stress. Of course, we have to complete our PDE here with initial and boundary conditions. And actually here we have a whole hierarchy of models. For instance, if you set the relaxation times to 0, you just end up with an elastic wave equation. If you set the shear modulus 0 and define the pressure as the trace of the stress tensor over 3, you get the acoustic wave equation. If you set mu equals 0, and if you allow positive tau sigma else, you get the viscoacoustic wave equation. Yeah, so you have a whole hierarchy of wave models. Okay, still, we are not finished with the modeling, because wave propagation in viscoelastic media is frequency dependent over a certain frequency band with center frequency omega naught. And one can use this fact, within this band, the rate of full energy over dissipated energy remains nearly constant. And the geophysicists use this fact to determine the stress relaxation times by a least squares ansatz. So we can safely assume that we know these relaxation times for a certain experiment. And now we can define the wave velocities, pressure and shear wave velocities, in frequency dependent in this way here. So here you have the moduli, pressure wave and shear wave moduli divided by rho. And here we have this additional parameter alpha, and alpha depends on the frequency and of the known relaxation times. Here is a simulation of wave propagation. On the top row, you see elastic wave equation without attenuation, and here you see with attenuation. Here, this is an isotropic elastic wave equation. Here, the fast, so the source here sits in the middle, and the fast wave, this is a pressure wave, and the slower wave here is the shear wave. And here you see attenuation here, that the wave is damped as it travels outside. And of course, we also can have here directional dependent wave propagation in anisotropic media. And the model also accounts for this. Okay, so let me define full waveform inversion. To this end, I introduce a parameter to solution map or parameter to state map, which maps our 5 parameters we are interested in, rho, Vs, tau S, Vp, tau P, to the wave field over a certain time interval, which is our observation time interval, our observation time. And we assume for the moment that this mapping is well defined. This means that the wave equation has a unique solution. Of course, we do not measure the whole wave field here. We can only measure it at certain time points, at certain the receiver positions. So we model this by a measurement operator, as we have also seen this morning. And I call my measurement operator not R, not M, but R. And it records our wave field here at finitely many times and at the receiver positions. So R applied to the wave field, these are our seismograms. And if you stack them together, you have a very large vector. Now, given a measured seismogram, find 5 parameters such this equation hold. And this is called the full waveform inversion of seismic imaging here in the viscoelastic regime. Okay, now let me show how full waveform in action, and hopefully it works. Should open now. Okay. No, let me stop it again. Sorry for this. I was too early. Too fast. First of all, let me show you. Let me explain you what you will see on the movie. Here it is one parameter inversion only. We invert only for the pressure wave velocity, and this here is a ground truth. And here on top you see our starting gas, which you can get from travel time tomography, which is a very smooth approximation, as we already heard this morning. And during iteration, it is a gradient-based method, which you will see. Here you will see the current iterate. And this here is a seismogram, which is measured when the source sitting here, so the red points here indicate the sources, and the green points are the receiver. So this is the observed data at shot position 2.6, means it's about here. If the source sitting here is shot, and then you see what the receivers on the right measure. So for instance, the receiver at 5 km here, if you take here the cross section, the vertical cross section, you get the corresponding seismogram. Okay, and this is the seismogram you get if you plug in here this parameter into our wave equation, solve it numerically, and generate artificially this seismogram. And here you see, and also this here will change during iteration, and this one will approximate here the ground truth, and this seismogram will approximate the correct seismogram here. And here you will see the time evaluation of the data misfit. And you will see that it decreases, but from time to time you will have a jump. And this is because the data are band filtered, and during iteration the band is increased. And each time when the band width is increased, you see an increase here. And basically what you see here is nothing else than the L2 difference of these two images, if you like. So now I hope I can get it running again. Should work. No, it doesn't. I'm sorry. Technical support is underway.
Want to play it again?
Yeah, please. Now I can click it. Okay. Thank you. Okay. So you have to solve a lot of wave equations, of course, for the forward and backward problem. It is on a loop. Not bad. Okay, I think you got the picture, and you can move on. Yeah, let me report some of our results. Basically, we have been interested in investigation of analytical or mathematical properties of the parameter to solution map, which maps our parameter here to the seismograms. So the first thing, well-posedness. We had to show that the viscoelastic wave equation has a solution. It is unique, so that we have a mapping here, and we could show that we have mild and classical solutions. We could come up with stability results and also with regularities results. And you need these regularity results to prove first order and second order Fauché derivatives. and also to get the adjoints of first and second order Fréchet derivatives. And here we could come up with very efficient formulation to speed up the computation. Further, we could show that our full waveform inversion is indeed an ill-post in the strict mathematical sense. And this also holds if R here is replaced by the identity. So the inversion, the ill-postness does not come from the measurement operator. It's intrinsically in the parameter identification problem. And yeah, the parameter here, the natural habitat for our parameters here is their infinity space. And so we came up with an iterative inversion scheme and a convergence analysis for this inversion scheme, which can cope with the L-infinity topology. And this is not a very easy topology. Implementation of inversion in time domain. This was known in geophysics in the frequency domain as wave field inversion technique. And in this approach, one simultaneously solves for the parameters and for the wave field. Well, let me explain this in detail. Assume that L is our differential operator, which depends on a parameter. So P is a multi-parameter. Can think of these 5 parameters here. And now we define the forward map, which maps a wave field and a parameter set to the differential operator with this parameter set applied to the wave field and measurement operator applied to the wave field. And now if we have our source term, if we have our seismograms, we now can here solve simultaneously for the wave field and for the corresponding parameter set. And there are several advantages come with this approach. One is that you do not have to solve a differential equation. Yeah? Here, if you compare it with phi r, here you have to solve. This is a so-called reduced approach or conventional approach. Here you have to solve the differential equation. Here you do not have to solve it. On the linear algebra, in linear algebra, this means you only have, so after discretization, you only have matrix vector multiplication. Yeah? You do not have to solve an equation. This is one approach, one advantage. Another reported advantage is that the nonlinearity phi all here is moderate compared to the nonlinearity phi r here. And this can be observed here. We did numerical experiments. This is a monoparameter reconstruction in the acoustic regime from transmission data. So here we have our sources on this side. On the left side, on the right side, we have our receivers. And we fix the density, and we just invert for the pressure wave velocity, which you see here. And then we started the conventional approach and the all-at-once approach with the same starting guess, and the starting guess was just here the background value in yellow, seen in yellow. And this is the best you can get with this starting guess from the conventional approach. This is the cycle skipping, which you heard this morning at least twice. If you use the all-at-once approach, you can get this result here. But it is known that if the conventional approach converges, it gets closer to the exact solution. And so we use the all-at-once output as input to a conventional Newton-based method, and then you get the result with a combined method, so which is, again, an improvement compared to the all-at-once method. So further, this is a result of our geophysics colleagues from geophysics. One can use here our second order Fréchet derivatives and adjoints to mitigate crosstalk. Crosstalk is an effect which is an effect that one parameter affects the update of another parameter. And this is, you can see here in a multi-parameter reconstruction. So we have here our 5 parameters, which are spatially separated, as you see here. The supports are completely different, and there are small inclusions within an otherwise homogeneous background. And this is a reconstruction you get with a first-order gradient-based method. And this is if you incorporate second-order information, which we provided. And I do not want to go to all these parameters, but only look at the density. The density here suffers by the first order approach here heavily under crosstalk from the shear wave velocity. Because if you reconstruct this here, you would think, okay, yeah, here the density is high here, which is not the case. This is crosstalk from the shear wave velocity. But if you use the second order information, you can incorporate it. You see that this crosstalk here is greatly mitigated. Okay. Now I come to the more mathematical part of my talk about the tangential cone condition. I will motivate it in a more general situation where we have a nonlinearity f mapping between Banach spaces, and we assume that f is Fréchet differentiable with f prime. We want to solve our nonlinear inverse problem by a Newton-like scheme, and you all know we start with a starting guess in the domain of definition, then we iterate, and to the current iterate we add an update, a Newton update, and this Newton update, Newton step, is somehow obtained by approximately solving the linearized problem about the current iterate. And the various methods around only differ in how they determine Sk from this equation here, from the linearized equation. So different the methods are, they often rely on the same assumption, namely on the tangential cone condition. And you heard it goes back to Ottmar Scherzer. Now it's 30 years old now. And sometimes it is called the weak Scherzer condition, because we have also the strong Scherzer condition. And the strong Scherzer condition is this one, if you have Q in front of F prime, right? Yeah. Okay, good. So what is the tangential cone condition? It is a local condition. It's locally in a point interior of the domain of definition. And it holds in a ball about x plus if for all elements v and w in this ball, the linearization error can be bounded by a constant eta less than 1 or even smaller times the difference of the images of v and w under f. Now you might ask, why is TCC important? Why do we need to use it? Because for a well-posed problem, you usually, if you analyze the Newton method, what you use is Taylor expansion. And the point is here, for an ill-posed problem, Taylor expansion does not give the correct local behavior. Have a look here at the Taylor expansion and assume that our nonlinearity f is completely continuous. Yeah? This is a reasonable assumption if you deal with nonlinear problems. Then f prime is a compact operator. And now assume that xk here converges weakly to x plus. Then this part here goes to 0 as k goes to infinity. However, this part here stays away from 0. So this part here is not the small part, but it's a dominant part. Can be the dominant part in ill-posed problem. And this is the point. And so you have to replace Taylor expansion here by the tangential cone condition. Or let's say it's convenient if you replace it by the tangential cone condition. Here's the schematic illustration. Here, horizontal line, this is our Banach space X, Banach space Y. The black line here is our nonlinearity. Now it's phi. And here now the tangential cone condition holds here in the ball this green line about x plus. U and v are in the ball. And the red hatched area here, this is a tangential cone about u here. And the opening angle is closely related to eta. Yeah? The smaller the angle, the smaller eta. And this has to, so yeah, and the tangential cone condition says that the linearization error here in blue has to lie in this tangential cone. And this uniformly for all u and v in this interval here, or in this ball, if you like. And from this sketch, you already can conjecture that the tangential cone condition should hold if phi prime at x plus does not vanish. Yeah? And this is, in fact, the case if you are in a semi-discrete setting. So we have the following result. Let theta be a mapping, Fréchet differentiable, between normed spaces. However, the pre-image space X is finite dimensional. And assume that X plus is in the interior of the domain, and theta prime, the Fréchet derivative, at X plus is 1 to 1. Then, if theta prime is continuous in a ball around X plus up to the boundary, then there is a second radius less or equal to r, such that first we have a local Lipschitz continuity in the ball, now with radius rho. However, we also have the tangential cone condition in this in this formulation here, where eta is now a function of v and w, continuous function, which vanishes on the diagonal. So this means we can make the number, the value here, less than 1 if v and w are not far apart. So if we reduce rho further, if necessary. If phi prime is a Hölder continuous mapping with of order alpha, we can estimate here eta just by the difference of v and w to the power of alpha. So we have a stronger version of the tangential cone condition. And now you may ask, of course, yeah, this is a sufficient condition here, but is it also necessary? And in this situation, it is also a necessary condition. Then, because if you have, assume that the tangential cone condition holds here from A, this weak version, and assume that theta x plus is an isolated value. This means there is no other point in the ball other than x plus, which has the same image as x plus under theta. So if this is true, then theta prime at x plus has to be injective. So it's almost equivalent. Okay, and now we want to apply this result to full waveform inversion. And here I first want to consider the acoustic wave equation, because this was our first result. So you always start with a simpler case, of course. And here is the wave equation. I already explained to you how you can come from the viscoelastic equation to the wave equation. We have replaced sigma by the trace of sigma over 3. So we have the pressure here, and this is particle velocity. We have still the density. And here this c is just an abbreviation for the p-wave modulus, which is 1 over c is equal to density times pressure wave speed squared. And now we have initial values here. And yeah, now the question is, when does this equation have a unique solution and a unique classical solution? Classical means that these equations hold here. And what we need here is that f has a certain regularity. It needs to be weakly differentiable in time with values in L2. C and rho have to be L infinity functions bounded away from 0 and bounded almost everywhere. If this is true, then we have a classical solution. So P and V are continuous in time with values in the corresponding L2 spaces, or we can trade in smoothness in time by smoothness in space. So it is a continuous with values in this Sobolev space. P is in H1, V is in Hdiff, and we have, of course, boundary terms here. Boundary conditions, Neumann boundary conditions, and Dirichlet boundary conditions. So now I want to apply my result to the parameter 2 solution map in this situation. But then I need a semi-discrete version, and then I discretize the L infinity space. If I do computations, I have to discretize anyway. Yeah? So this is a natural approach if you do computations. And so so L infinity now is replaced by this ansatz space. We have m basis functions which have a certain regularity. And then I need something which Barbara also assumed in the different version. So we assume that our basis functions here are locally linear independent. This means if you have a linear combination which vanishes on a subset of D with positive Lebesgue measure, it has to vanish everywhere. So if it vanishes locally, it vanishes everywhere. And concrete examples for such spaces are the polynomials and radial basis functions. Yeah? And for the radial functions, you can use the exponential, the Gaussian, or the inverse multiquadratics. Good. Now we redefine our parameter to state map a little bit. We have our parameter C and rho, and now we want to initiate our source, of course, only in a certain domain, yeah, where we can initiate our sources, the source positions, so to say. And we only can measure our waves here at a domain omega, which models our receiver positions. So we map our parameter CR to the map which maps an admissible source to our wave field initiated by the wave equation restricted to omega. This is our parameter to solution map. And this is a semi-discrete map. Yeah? So it maps the parameter space into a space which maps a source to a wave field restricted to omega. And yeah, if you want to apply our lemma, we have to show that phi is Fréchet differentiable and the Fréchet derivative is injective. So what is the Fréchet derivative? The Fréchet derivative, evaluated at C and rho, is a mapping which takes two arguments in V, in our finite dimensional non-subspaces, and maps it to a mapping which maps a sequence, a source, to a wave field. So phi prime at C rho is applied to H1, H2, and this is a mapping which maps a source to a wave field. So we can here apply a source, and what we get is a wave field. And this wave field is a unique solution, so the wave field restricted to omega is a unique solution, again, of a acoustic wave equation. Yeah? It's the same wave equation here. However, we have different source terms now. Here, the source term is made up from H1, H2, and the original wave field. This PV is the wave field which we initiate by firing the source F. Okay. Now we can show the following. We can show injectivity more or less. So suppose we have an H in V2, so two components, at least one component does not vanish, and assume that sigma and omega are disjoint. Yeah, where we fire the source and where we measure, this has to be disjoint sets. And assume that our observation time is sufficiently large. Then there is an admissible source, which here has support in sigma, such that the wave field associated with the Fréchet derivative does not vanish on the receiver set, so to say. And this F does not depend on H, and it only depends on the C1 norm of the pressure wave velocity. So the point is here, it only is sufficient that you excite one source. You can excite one source if you know it. Yeah, it depends on your material. But in principle, it is sufficient to excite one source to have uniqueness, local uniqueness. Yeah, if D is convex, then we can have a lower bound for T. So what does it say? Here it says the T has so large that if you fire a source in sigma, the initiated wave has to be able to reach all of D in the allotted time. This is the geometric interpretation of this quotient here. Okay, and the proof here is twofold. We have two steps. This is the tricky step here, and it's really not so easy. We use Holmgren's theorem and propagation of singularities to show that there is a source such that the original wave field does not vanish at the receiver positions. So let me go back. So this means we have to show that we can initiate a wave here which travels through omega. This is what we show here. It seems to be trivial, but you have to, yeah, everybody would say, yeah, of course it does, but you have to show it mathematically. And okay, so we have this. And now assume that we fire this source here, and we assume that the wave field, which belongs to the Fréchet derivative, does vanish at the receiver points. Then this means, if you go back to our equation here, this means that this part here is 0 in omega, and so the source is here. The source terms have to be 0. And so we have these equations. But now recall our funny space V. Here, H1 and H2 are locally linearly independent, so they cannot be 0 on omega without being 0 everywhere in D. Yeah? And so this means that the time derivatives of P and V have to vanish in omega. And now we recall that our initial that we have 0 initial conditions for P and V, and if you integrate, you see that P and V have to vanish in this space-time cylinder here, but this is a contradiction to part 1. Although this cannot happen. And so phi prime is injective. And this is true for any C and rho in our domain of definition. And now we have our theorem. We have that for any C plus rho plus in the domain of definition, there is a ball such that we have Lipschitz stability, and we even have tangential concondition in this slightly stronger version. Yeah, and the proof is from the proposition just explained. We have that phi prime is injective. We have to show, and we can show this, that the mapping here is Lipschitz continuous. This gives us here this stronger bound here. And finally, we apply the argument, and we are done. And yeah, meanwhile, we also could prove the same result for the viscoelastic wave equation. Yeah, so I should be happy, but I'm not. Yeah, as a mathematician, I think you are never happy. Yeah, I'm happy for my personal life, of course. I'm happy that I'm able to do mathematics. That's the point. Yeah, but of course, yeah, something drives you. Yeah, drives you forward. So I'm not happy with this, because why? This space V is somehow artificial. Yeah, usually your colleagues from numerical analysis discretize the wave equation by finite elements or by discontinuous Galerkin method. And then they give you a mesh, a decomposition of omega. And the natural space would be to approximate your parameters on this grid by piecewise polynomials, for instance, or piecewise constants. Yeah, and this is what I like to prove. This is a challenge. So assume that we have decomposed into subsets here, usual, and now we replace our space, our ansatz space, by characteristic functions with respect to dj times a polynomial or a constant, whatever you like. So here we have piecewise constants. Now we replace the former ansatz space with this ansatz space. Works perfectly. We have the same, of course, we have the same Fréchet derivative. Yeah? And here you see H1 and H2 and are now here. The point is now that H1 and H2 have compact support. Yeah? And what we have to show now is that we can initiate a wave here, which travels through the medium, reaches H1 or the support of H1 or H2. This we can show with the arguments I just used for the proposition. But now we have to show that the wave, which travels here, yeah, initiates a wave for this new wave equation, or acts as a source, such that the wave initiated here travels through the medium to the receivers. And this is the tricky part. We know that the source terms are active, yeah? That is, we know. But we do not we have no control over these sources. We cannot say, yeah, the source initiated by this internal source here travels to omega. So we strictly conjecture this to be true, but the proof is still missing. So this is work in progress. And now let me conclude. So I have shown you that full waveform inversion is a nonlinear ill-posed problem of recovering the parameters in the underlying wave equation, in this talk, the viscoelastic wave equation, from reflected wave fields. And I've motivated that the tangential cone condition is an important ingredient in the convergence analysis of a variety of inversion algorithms for nonlinear ill-posed problems, such as full waveform inversion. And we have seen that the TCC holds in a semi-discrete setting if, and almost only if, the Frege derivative of the nonlinearity is a one-to-one. And I've shown that the tangential cone condition holds for full waveform inversion in acoustics, even viscoelastics now, for a discrete parameter space using global ansatz spaces and the local ansatz spaces, maybe in 1 year or even later. So thank you for your attention.
Tangential cone condition. Sorry, I have to ask this because just before I said I don't believe in the tangential cone condition holding for boundary measurements.
Yeah, we take the measurements inside. It can be very small, but it has to be positively back measure. Omega has to be positively back measure. We do not have boundary measurements.
And probably also you don't drive the discretization to, you have finitely many.
Yeah, if you increase the number of basis function, what happens is that the constant grows, and the constant in this Lipschitz stability also grows.
Yes.
So we do not have a control of it, and I doubt that it will be bounded.
Yes.
Yeah. This is a finite dimensional phenomenon. But if you do computations.
Yes, that's what you indicated with piecewise contributions.
Yeah.
Yeah, very interesting talk. Could you go back to the all-at-once method? Because of course that found that very interesting. I was wondering, like on the computational side, it was a bit. I didn't quite catch. What would you need to implement, or how is that?
So the what you need to implement is if you apply here, let's say Newton method. Yeah.
Right. So you.
And what do you need? The Frege derivative, and then you have to apply. You make to solve. You only have to apply the differential operator. So the matrix discretizing your differential operator to a wave field.
Okay.
If you use and of course you have to solve the linearized equation, right? But you use let's say Chamrez or something like this, and then you only need matrix vector multiplication.
Okay. But I mean that sounds.
Yeah, but be careful. Be careful. You need preconditioners.
Okay.
Otherwise, it does not work. So the implementation part here, one of my PhD students did it, and this is very tricky.
Okay.
Yeah.
And in principle, you need to keep like then the whole sort of wave field in space at time. It becomes an explicit variable, and you need to.
From a theoretical point of view, it's very appealing.
Yeah. Okay. Thanks.
Yes, I'm. As you know, I'm also a big fan of this all-at-once.
Yeah, I learned it from you.
I know. I'm also aware that it was first appeared in this full wave literature. But actually, the question that I keep being asked is about storage. Yes, because people say, well, then you have this U and the P that you have to store, and it's too much. But when you were able to solve this problem.
Yeah, but you also have to store the parameters here in this approach.
Yes, but if you have U, then you have a function of space and time that is also that you have to keep as an iterate somehow, isn't it? So in the reduced approach, you don't only have the parameters.
I would have to ask my PhD student, but I think computing time was a problem, not
Yes.
so slow convergence, but not memory.
Yes, so there's a certain trick that you don't need to store U for all space and time instances, because that's what I always get criticized for. And I would really be happy to say, no, there's particular.
I cannot answer this question, definitely.
Let's just talk about it.
Yeah.
That's another talk if anyone's got one.
The whole talk.
Sorry, question. Okay, let's go for a cup of tea. So we're back at 10 past 4 from Mark Anastasio. So thank you, Andreas.